a NERI experimental facility. And we have our large mobile shakers, and our logo is T-Rex, but the nation is our laboratory. Have mobile shakers, will travel. So that was when I was young man. Paladin had what was it? Paladin had have gun, will travel. Huh? Well, we have shakers, will travel. The co-principal investigators are Brady Cox, who is working hard, and Patricia Clayton, who is working hard. So somehow the boss got all the work here. Huh? Okay, so I'm here, but I would be here anyway. And again, we thank Dennis very much and Kim very much for, we wouldn't have it without them. So next, please. We'll go faster. Okay, that's probably 15 years ago. I need to update that. But at any rate, there's Brady Cox looking just as young as he does now. That's Patricia Clayton, who's even younger. This is our dean, who's free, but she's a part of the project because she gets fully paid, so we get her for free. But it's good to have the first chief in the line to sign off on things to be a part of your project. Okay, there's Fan Yu, but also Michael Mung. Does it say Michael on your passport?
Yes.
Okay. Andrew is not here? Okay, he's relaxing. Good, good. Okay, an operator. There's Robert, and Cecil is part-time with us and a very important advisor. And Cecil can walk up to a shaker and tell you if it's running properly or not, just by listening. That's not much of an exaggeration, is it? Yeah. Next, please. You know, I don't know what this is all about, huh? You know, okay, here we are, just what I described. Elisa is one of our administrators. In fact, that's who you're sending stuff to. Go ahead, Fanyu.
The TACC, I think this slide is about TACC.
This over here? Yeah.
CI, all the data we collect in Columbia with CI, so it's called design safe. So if you register, then you can see all the data we collected. It's not, we'll put it on next week, so you'll be able to see all the data we collected in the field, including the video I can show you and how to process it. We give it's called Jupyter Notebook. It's written in Python, and then you have explanation what it is, and then show you the code, like we can run it, so you can actually see the data yourself without much work. That will be on the internet next week once we get it.
And for you modelers, we also have up there already the levy that we did last year in St. Louis, and the data is all well documented and available to anybody in the United States that wants to use it. That's a fair statement, isn't it? But I'll have a video here, and I'll show you some data that's never been used, as far as I know. That's for nonlinear modelers is really special. Fan, you can probably explain some of these better than I can. That's a simulation center.
I'll later on at 4:30, you're going to go see the wind side right here at University of Florida. They have a wind tunnel, and they also a centrifuge side of a full waveform tank, which is the tsunami side, and also a couple shake cable, one shake cable, and a hyper simulation testing structure also. So that's 7 equipment sites. Is our equipment side, our ES. That's fine. NCO is the one who do the scheduling. If you've got a project with us, you need to check with NCO and scheduling with that. They're just trying to be fair, so we will not treat you differently, but we never treat you differently. It's always first come, first served.
But you check with us first. Yeah. They don't tell us what to do. I probably shouldn't say. We schedule, and then they put it on the schedule, but make sure that you're treated fairly.
Yeah. Sim Center is the numerical simulation in
Berkeley, yeah.
And then also there's a user forum, so anybody, all the user, previous user will create user forum, you just double check it with
yeah, you could complain there. Or you can complain to Professor Woods, and that would also zing us. You know, I mean, you have plenty of places that if we're not treating you properly, you can complain, and that's fine.
The
because we want to treat you properly. We will try to contribute to your testing, because we've made lots of mistakes in the field. So we'll try to tell you what not to do. Okay, next. And I know these slides, but I'm just saying, do we really need to talk about them? You know, do you have anything you want to add there, Fanyu?
No.
It's TAC, but TAC isn't this Ellen and the supercomputer and so forth?
Yeah, they're also located in UTexas.
So we have tremendous computational horsepower with the supercomputers at the University of Texas. I guess they're called the Texas Stampede.
Yeah, that's one of the computer called Stampede, yes.
Okay.
And now it's Stampede 2.
Yeah. They just got another 20 or 40 or 50 million. Yeah. So and I know Cox and a lot of his work is using it, and it can tell I did 1 million solutions and do and so forth. Next, please. So this is just to give you a feel. This is our main campus. This is this is now called our Pickle campus. Now it's not Heinz 57 Pickles. It is Jake Pickle, who was very helpful to the university over his career in Congress, in the U.S. Congress. We'll leave it at that. And that's where we house all of our equipment and build things if we have to, which means small sensors that we'd be pushing in the ground or things like that, because we'll do a lot of that as needed. Next. We hear you.
I think it's someone else on the conference.
Maybe they want to chime in.
You are in a Zoom meeting now. There are 4 participants in the meeting. This meeting is being recorded. You are muted. You can mute or unmute yourself by pressing star 6.
It'd be much worse if I were doing that, so let's just be happy here. Okay, well, go ahead and flip to the next one if you would, if you can, while you're doing that other. All right, so at the Pickle campus, you just went through a whole bunch of slides. I'm a fast talker, but not that fast. Okay, so here we go. As part of NEES, to get started, we were going to build a building, and then the university saw what it would look like, so they gave us a building that in fact looks worse, but it exists. So we refurbished that, and this belonged to our structures lab, and they gave us half of this building, building 46 out at the Pickle campus, and you just see some of our equipment there. Boo, what's that? It is. That yellowish thing is a different vibe that we have for a different purpose. But all of that is ours, and this is paved. Much of this is paved now and so forth. And it's a very good place, and we have some parking and so forth next. Not a big deal, but the university has been good to us in helping us that way. Next, please. Yeah, so this, looking into the back of it, there's the RDD, rolling dynamic deflectometer. That's Thumper, and that has to be Liquidator, doesn't it? Unless it's a real old one. It's Liquidator, okay. And you'll see what those are in a minute. Oops, back please. And this just shows you a plan view of it. Those are the big doors. And we have lots of space where we have fill it up with equipment. And this is an air-conditioned, one of those...
It's a lock-in.
Yeah, container. A container, but this will certainly get to 130 degrees in the summertime, and there's poorly blah, blah, blah. Here we are at work That's Cecil, that's Robert. I'm not going to say, oh, who's that? I don't know. I know who that is, and I'm not going to say. I took the picture by accident. But here, all of these things are cables where we built. These are pore pressure transducers. They were 2D, and then we went to 3D with small geophones. You'll see those, building those so that we could push them in the ground and shake the ground and measure motions and also pore pressures that might be generated. Next. So this is what we have to offer you. T-Rex is a triaxial shaker. Everything that's white there holds down that little orange stuff. It was supposed to be a burnt orange, but that was the first one made, and they gave me a Tennessee orange. But it's too expensive to repaint. But that's been repainted. How much did it cost, Van, you to give? We haven't? Which one have we? I thought Cecil did one.
Raptor and Rattler.
Okay. I think we repainted one of these, but we won't go there. Okay. But, you know, it's all hydraulically operated. There's a big engine in the back to power the pump. It weighs about 72,000, something like that, 70,000 pounds after new things we put on the back. That's a hydraulic ram that you'll see on the back. Liquidator also has one. There's a ram. T-Rex, you can push a button and change the mode of vibration. So it's probably the only operational triaxial shaker in the world, although the Russians bought 3, but we don't know if they're working anymore. But that really makes it very nice when you want to do P and S. You got one machine and it does all of that, PS and Rayleigh. So that's very helpful that way. Liquidator, and yeah, I named them, I should have done exactly the opposite. But Liquidator is a low frequency shaker, and a low frequency shaker, that's the only one in the world. So typically a vibrocyte has a stroke something like this, whether you talk about vertical or horizontal. It's 4 inches or on that order. This one has plus or minus 8, and it has meaning that it can go much lower frequency. So it was built just to go low frequency to generate long surface waves. We'll have a little. It was built to go to 1 hertz, but you're going to see it lower, and it will be demonstrated. But see, this vertical mode is 60,000 pounds. Now, it's going to show you half in shear because of friction. I mean, it's going to start sliding. You know, coefficient of friction of half. That's what they say. So you got enough force. This is a little bit more than that, but I mean, you're almost lifting the machine up, huh? When you start shaking with this machine and you have most of that vertical load on it, the tires will do this because the ground's doing that. It's quite impressive. Well, at least to a little guy like me. And just for the record, my grandchildren have ridden in all of these, you know. I mean, now that's a really big deal. I mean, actual blood line grandchildren. Okay, not some of other grandchildren. Okay. I'm not allowed to drive the darn things. Maybe for another reason. No, I'm just kidding. So this is a very nice machine. If you want to, we can probably profile, depending upon the system, down at least a mile. We'll get to that in a bit. And here's Thumper. Thumper is, you know, so you can go in the cities and vibrate a bit and not have lawyers come out to sue you, because they love to see those. But this sort of hides, except we had this working right next to a building on the UCLA campus. You know, we got up close to the building. Holy mackerel. This was like a 7-story building. People came running out hollering, huh? What are you doing? Because they thought it was an earthquake or something. And it was just this little machine, so we had to stop. Yeah, they had no sense of humor. So we stopped testing and moved away. These are 2 shakers that were given to me by Lawrence Berkeley National Laboratory. We worked for about 9 years. We worked 10 years total, about 9 years going out to Yucca Mountain and shaking and looking around the mountain. and they sent 5. These are 2 that we have operating, and these machines were going to be cut up for scrap if they didn't get rid of them. So they were very nice because we had been working with them, and they now use this T-Rex when they need it. But Raptor is just vertical. Rattler is just horizontal. And we also have a 26-wheeler that's Liquidator or T-Rex there to move them on various projects. Now, sometimes we don't move them, sometimes we do. But it's very expensive if you have a bunch of sites that you need to go to with that machine, and you're going to have a rental truck there that is just sitting there waiting for you. So this, you can work for a few days at a site and then move to another site and so forth. And that's how come we have that, primarily. We're not any more cost effective in moving it around compared to hiring a firm. Isn't that right, Panyu? I mean, it's about the same. $4.50 a mile?
Yes.
Something like that.
It's not an SF price is closer to just ship it by outside and maybe cheaper. But if there's an SF project,
we're going to try to get, don't tell them the number. We're going to try to get more. I think is it $4.50 a mile? No, it's 40. Yeah, it will show you, but it's all on the web page. It's easy to find out. No, then you save a lot of money, yeah, on the NSF project. Okay, then we have field support trucks. This also has a tank for diesel fuel so we can refuel in the field. At one time we were paying to have trucks come out from local areas and when they would come and blah, blah, blah. So you have to have all of this stuff. We have air-conditioned space for you, and that just shows pushing some of the equipment in with a newer RAM that we put on there. So here's T-Rex. These are all the machines I just described, and here's T-Rex in terms of the vertical forcing function. Here's a horizontal forcing function, and the scale here basically is that's going to be closer to 300, that's going to be closer to 150. So there's the factor or 2 without getting into too many details. This is Liquidator, and Liquidator is designed so it can be horizontal as well as vertical. But we've never had it horizontal because it's always been so busy vertical. It'll take a crane, a big crane, to orient it horizontally. And a day maybe, a day and a half, 2 days. Is it a day, we think? We've never done it, so we're not sure. But we think something like that. We'll show you it operating. They're all about the same. That's the same, basic body moving the shaker around as T-Rex. Next. This is going to be a video. This shows, hang on for just before you start it. This shows you T-Rex in New Zealand. This is in Christchurch. $85,000 to get it there and back. Brady tells me it's a smaller number. Or do you tell me it's a smaller number? It's what?
60,000, roughly 30,000 each way.
I like my number better, but okay. Yeah, so I misinformed a lot of people. But it went through the Panama Canal, not the Suez Canal. The Panama Canal, and it's impressive when it starts shaking. Go ahead, and Brady was using it there. Whoops, sorry. Brady was using it there to do surface wave testing. In this particular case, we used it for liquefaction. There's video with it. I don't know what's going wrong.
It's shaking now.
Yeah, it is shaking. Yeah, that was true too. There's not quite this much shaking though.
So it's hooked up to the internet. So it's determined by how fast the webcast can go. So you can see the water going ripples like that.
You can see it. You'll see everything is moving around there. There's Robert. I think he goes back again. And so we're seeing if we can. Yeah, it's impressive when you see what it can do. We're not putting it on top of a sinkhole. I don't care if you tell me it's a small one or not. Just for the record, Oh, I'm okay to sink it in a liquefiable deposit, but I'm not having it drop into a sinkhole. Don't you still have some Corvettes in sinkholes here in Florida? Or did they get them all out?
This far north, we don't get them.
Oh, okay, good, good. I'm happy we're here. Next, please.
Tomorrow at our site, most of the sinkholes are pretty small. Not those house-sized ones.
We'll squeeze Mung down one of them, no problem. Okay, here's Liquidator on the top of Yucca Mountain. But, you know, that was T-Rex. Here's Liquidator. It is force limited. Now, not because of the big strokes and that it has. So it's force limited. So it's got the same output in horizontal and vertical because the machine's heavy enough to hold it in the vertical mode to generate the same force. What you do see, though, you're going to see a special vertical. It couldn't be horizontal, but a special vertical configuration, and that even takes it down to, do we have it right, Fanyu? Is it 0.7 more or less?
0.7, 0.6.
Yeah, something like that. So we generated a 2-mile long wave with that. Now, we didn't realize we could, and so we didn't have our sensors out far enough, and you didn't get a chance to go back and do it again. So, well, that's one of those mistakes that you regret, but we still got down in excess of 2,000 feet, and we got down to true bedrock on the East Coast, 9,300, 9,500, 9,600 feet per second, huh? And they were so happy. Here it is at 1 hertz. Go ahead and hit. There's going to be a video here, and that'll just show you. So, yeah, it's smooth, but you know, just gives you a sense for, that's in Imperial Valley of California, but it just gives you a sense about that's on the order of 1 hertz, and there the waves, of course, would be shorter because it's a much softer soil. So you get a frequency, but you got the velocity of the soil. In Columbus, Georgia, the soil, even the soil part, was much, much stiffer, and the rock is close to the surface. Next. This is a special mode. So go ahead. Yeah, it's smooth. It's smooth. I don't like this. So for about 3 years, maybe, I was after Mung. I'm telling him, Dr. Mung, I want to get low frequency. Do we need this? Nah, it'd be huge. Okay, can we do this? And so in the middle of the night, one night, I popped out of bed and wrote down this thought, we'll lift the whole dang body and have the plate not do anything. We have now 55,000 pounds, not 15,000 pounds to lift. So even though it's much slower, we still get good, strong force levels. And so Professor Cox was at the same site with us in Columbus, Georgia, and he did his fancy ambient stuff with a mile diameter or 2 mile. Our waves were just as longer than his. Now, it turns out they agreed, and apparently there's 2 solutions in the seismic area that say, I mean, in the seismological area, that one says this and one says that, and apparently we're going to debunk one of the solutions, according to Cox. That's as much as I know, but it sounds good to me. And I'm sure there are solutions out there that should be debunked. Because they have never had that type of information. Next, please. So, getting to smaller, and you're going to see this is going out to Portland, Oregon. Okay, another thought. Any project that's coming up is on the web page, on DataSafe. Oh, the NCO. Well, but also the NCO.
Our website, you Google NERI UTexas, you'll find our website, and you can find what project we have.
So you can see where we're going to be working. If you want to piggyback a project, not Sinkhole, because we're not in Florida right now, but if you wanted to piggyback a project on that, you can go and try to get what would be a rapid or something. I don't know what they would call it now, but you can try to go, and you would save a ton of money. You don't have the transportation. You're not flying people back and forth. Let's say if we can work it that way, we would stay out there and do extra work for you. Now, we're going to be in Portland, Oregon, and we're not sure exactly when. So, but it should be in the spring or the summer of next year. We're going to be looking at liquefaction of silts with some plasticity. And that's a big unknown. I think gravels are more unknown, but that's a big unknown. And we will have this machine as well as T-Rex. So we now are going to phase them together. So they can be phased like this to make it bigger. They can be phased this way to be like a gyratory loading, and we'll be doing that in the field. I had to come up with a new idea to try to get funding. So that more than doubles our amplitude this way. But no, it's a very nice opportunity. And piggybacking, again, all of this data, now since it's a funded project, the data doesn't become available immediately. It's probably a year delay or something like that. But all that data still becomes available. And I'm going to show you, as I already said earlier, some data that's out there that no one has used, and you can see if you have any interest in it. Thank you. And, you know, Rattler is just a horizontal one. I said that wrong, didn't I? You can correct me when I do that. That's who's going to be out there, because we want two horizontal shaking, and I was doing this, right? But I had this and this. Sorry, I can't do them together. So there's Rattler. That's what's going to be out there, and so that we can shake in either a larger area, which gives you more strain, or phase them at different phases together. Next, again, Thumper. And so you see Thumper, we just have small amplitude force levels that we can apply. And it's on the back here. It's a little shaking mechanism. You'll see it in another project. Each one of these shaking mechanisms is built to be taken off, well, not Raptor and Rattler, but the ones that I had built for us, those are constructed so they can be removed from the machine. Now you'd have to bolt them down or something, and that's a big deal. That's not trivial. But you can attach them to a structure, and then the machine is still there to power them, and we have a lot of hose. Now you can only have so much hose until you start having a lot of loss in the hose. But we've been talked to by structural engineers that might want to put them up, and of course they would lift the whole bloody truck up then. 50 stories with cranes on buildings and stuff to shake buildings. Because we just did a workshop with Nanat Gagunsky at Rutgers on a bridge. It worked well, but we blew a couple seals, so we didn't maybe accomplish everything we wanted to, but we accomplished everything they needed. Because these machines eat themselves up. It's not, these are big machines. And the bridge is moving. In fact, the best example is Professor Woods sort of jumped and walked off the bridge because it was shaking. So was that not right?
I was chasing you.
Oh, that was it. I don't know. It was the bridge moved, I'm telling you, and you'd see the bridge moving and the abutment not and so forth. And it was so holy man. Yeah. Okay, cut the force down. Mung goes crazy on some of these things. Cut the force down, cut the force down. It does worry you. I'm getting sued before he does. So, you know, it's...
His house is uncollectible, so he guarantees it. So.
It was interesting, and I wrote a proposal. I was a flea on the tail of the dog with Joel Conte about shaking bridges very early on with T-Rex, under the NEES, and we went down in smoke. We got as bad a reviews as you can imagine. We never tried it again until Nanat came along and got it funded. Frank Moon, I have that right, don't I? The structural engineer there was explaining to us. I didn't know enough, and Joel wasn't really aware of it, because the other people, we went down in flames because they said they could do it with ambient vibrations. With ambient vibrations, there's a stick slip. I should be talking to these guys, forget you guys. There's a stick slip phenomenon, Florida DOT, a stick-slip phenomenon there. Ambient doesn't get it to slip. It's in the stuck mode. So when you get it in the slip, the natural frequencies decrease. And that's what you really need for the earthquake. Trying to figure out what the earthquake's going to do, because having even more slip, huh? I don't know how nonlinear that slip is. And we didn't do a whole bunch of different levels. We were just a trial basis to get us started, huh? But yeah, there's some, that's all available.
Yes.
Is it already there?
No, there's their project. So
You're right. They had an NSF project, so that, it'll be a year before that will probably become available. But I mean, you can't get this data or this understanding in the laboratory, I guess. I think you might be able to with some bridges, but some large scale. But it was very nice to hear him talk about that. I don't know how I got off on that tangent, but it has to do with some of these shakers and taking the equipment off. Now, T-Rex on the bridge was no problem, huh? I mean, it was fine to have that load on the bridge. Next, please.
By the way, if I might interrupt, Thumper, in fact, is the device that's parked in the parking lot right back here. You'll be demonstrating that tomorrow at the site. So,
Anybody that wants to interrupt at any time, please do. No, I mean, this is a conversation. It's not meant to be anything but that, to try to help all of us. And that's just a beautiful picture to me. I like a shaker on a 16-wheeler. It just probably is something I didn't even realize that I've dreamt about since I was 6 years old, maybe. Next, please. Okay, again, this is really important to us, that we can send someone off to get fuel while we're still working and so forth and so on. Here's a trailer that we have replaced because the other one was a little too small, was blowing tires, or we put too much in it. Doesn't matter which way it goes, we changed it. This one has to be changed now, and that's going to cost us about $65,000, but we think we have program income to do it. Sometimes Dr. Mung answers yes to these, and then I find out later we were maybe a little short, and I'm the responsible party, but we won't go there. We have the instrumentation van too. We have another small trailer and so forth. Next. There's Professor Cox, younger. In the instrumentation trailer, the one we have is now even a little bit bigger. Is it the same size? Okay, but just more robust for the axles and all that stuff, yeah. And that Sun Moon Wong, and they're in there with, so we have 72 channels of one digitizer. Mung can speak to these better than I can, at a 50 kilohertz sampling rate, 64 channels of this data physics, 24-bit, up to 200 kilohertz sampling rate. I know various folks have tried to replace these with National Instruments, and they can't compete yet. I'm sure someday they will, but this is still, you know, first-rate 136 channels of data acquisition, and that's a big deal. Next. We have lots of sensors, 1 hertz because of surface waves and the things we like to do. 1 hertz sensors that are vertical as well as horizontal. You know, I don't know if you know, they would sell you these as 3-component sensors, and we bought a couple, and it's just not good. Let me say it that way. The way they couple them and everything, they have natural frequencies that generate in the system that you're recording with and stuff. So ours are all separate when we're putting them down. And what you see also, just for the record, so let's say we were doing this on a pavement, but this is even in soil. That's a little base that we have developed, and Ivan Wong and others have given us good ideas. So we've we're happy to take good ideas. But it's spherical shaped, so you can set it on something where you have it, at least it's got a nice strong coupling with it. You can feel that, huh? Then you put your sensor in, and you got your level, and you can adjust it now, and it levels up just like that. Whereas if you're out in the field otherwise, it takes much more time to get the darn things placed and leveled and so forth. So that's been very helpful to us. Obviously, this is Professor Cox, because I don't have all those takeouts, and the cables that we develop, we'll have them shielded the whole way. There's some Trillium compact broadband sensors that, once again, Fan Yu is our expert in some of these things, but, you know, 120-second period, I don't know that you're ever going to need that, but, you know, you're certainly, with this, Brady got down, I'll show you that, Professor Cox got down deep in Christchurch because of the ocean waves. Right next to the ocean, right next to it, huh? And yeah, that allowed you to get some very nice low frequencies. Although in Columbus, Georgia, you could tell the waves, the very low frequency ocean waves hitting the land. So you'd be surprised. It's really helpful also for site resonances, looking at resonant peaks at the sites. Next. Again, you know, we have cone penetration sensors for you. So you talked about those. I think this little one not going to let you push in just any old place. It won't go in gravel either. But, you know, these are a bunch of Fugro cones, pore pressure transducers, things like that. We don't use the triaxial MEMS accelerometers anymore. They're very expensive and so forth. Now, we do use the little accelerometers, let's say, from the phones, but that would be in the bottom of a sensor like that for tilt. So as we're going in, measuring tilt. But we build our own sensors, but I'll show you a little bit more. So that's what we needed, a pushing mechanism, so we didn't have to have another device out there, some other big machine. So we could do more with just one machine than we would be able to otherwise. And I think that cost us about $40,000 or $50,000. 35? Gee, every time I've given numbers, I'm exaggerating, aren't I? That's right. That's right. When I talk to Florida DOT, the numbers are getting bigger. We try to stick together. See? Okay, next. Yeah, now you know you can borrow instruments. This is NSF supported, but it takes a little bit of work, but they're free to NSF funded projects. And one of the very first projects we did was Simon Kempler and from Stanford. And where were we? I wasn't there. Yeah, okay. And they had all the Texans, they called them at that point. Those were 4.5 hertz phones, though, weren't they? That 3D that stand alone are battery operated, and they spread them out all over the valley, and they had T-Rex go shake in different areas. Huh? That data is available too, isn't it? Yes. I don't know how good it is, but okay, is that old? It's
Iris is really good about helping you.
Yeah. See, they're very good about helping you, also training you, right, on some of those things. Yeah.
And they basically have librarians for the data.
And you're free to say more, because you would be happy borrowing from them, right?
Yeah.
Yeah. I mean, you need to do it in advance. I mean, there's not a pecking order. It's just that it's busy, and you have to see if you can get yours in a time. You know, you just have to work ahead of time. That's all. We're giving everybody these slides, aren't we? If they want them. So you don't have to. Yeah, you don't have to write any. I'm sorry, I saw you writing down. You don't need to. You'll have all of this. This is when this mobile shakers will travel. And we had 50 projects over our NEES shared use industry government effort. And this just shows you where we've been around the United States. In Hawaii, that was a particularly a nice opportunity where even my secretary wanted to go and was upset she wasn't allowed. Teresa didn't get to go help. Yeah, that'll just get you in trouble. And Christchurch, New Zealand, and that was really a very special one. Next. It's a lot of fun when you have this equipment, and the National Science Foundation will require of you to do this. And that is This is Explore UT. So here's T-Rex. It's here being demonstrated when open house is around, and that's a very, very large group. But I mean, during the day, we might do it 10 times at least, and it would vary from 50 to 150 or so people. Are you here, Mung?
Yes, somewhere.
Yeah, me too. I can't. Is that me? I see a white beard and I see a Texas hat. I think that's me. But that Cecil, yeah. No, it's a lot of fun. And so I got the really great idea. I was the only one that thought that. I got the really great idea because whenever you demonstrate to kids, what do they care about? How tall they are relative to the tires. I am not teasing. They don't pay any attention to what you tell them. They don't care at all. They see you're excited, so NSF likes that, and they go running up there. So I wanted to take on Texas, okay, we'll have your next to the tire, we'll take your picture, you give us your name, we'll put it on the webpage, and you can pull it off. Oh, you can't do that. You can't take a picture of a child and put their name out there in space, huh? Yeah, I know. Well, I wasn't that smart at the time. I didn't take any pictures, you know, so okay, but it's like, no, you can't do that. What? Just shoot those guys. I'm sorry. That was an editorial comment. Okay, this was at a conference. Are you there, Dick? Yeah, Dick's at the conference, but this is SAGEEP, and we were demonstrating at a conference. This is deep downhole testing at Pacific Northwest National Laboratory. T-Rex is a great source for shear and for P going down 1,000, 2,000 feet if you have boreholes. Huh? Really an outstanding source. Here's a landfill, and yeah, we all are in all kinds of stuff, and then our moon suits, and that's T-Rex, and that's Thumper to be different force levels that they're shaking on a landfill. This is one I particularly enjoy. That's me, Julia Roberts, Andrew Keene, Emily Gibson, Brady, Mung, and I guess Rich Lee he's there. Oh, there's Andrew Valentine, isn't it? Yeah. Okay. You know what those are? Hoodoos. Those are precarious rocks. Now, this wasn't on the Indian reservation. We were not allowed to go on the Indian reservation. So they're very sacred to the Indians there. They hold them as special. But the geologists, seismologists, and so forth like to see these, and we would shake them to see, not if we could tip them over, but what natural frequencies they might have, because how long have they been in this shape? Well, then no big earthquakes of such and such have occurred in this amount of time. And so, yeah, we did that just a couple years ago now. But it just gives you an idea of all the different things you can come up with. I wanted to hook, you know, you'll see in a minute the big mechanism. We have the winch on the front and to a building and sort of pull it over and let it go, huh? But they didn't think much of that at Lano. I think it probably was some of their top secret stuff, but it was a very interesting looking building that we could have shaken. Next. And so it never ends. There is Thumper on the top of Mauna Kea and on the big island of Hawaii. And at that point, Cecil almost couldn't get it back up. And didn't we get a bigger engine at that point, Mung, because of that? Yeah, I think we had to replace the engine because the air was so, the oxygen content, yeah, was so low. This is Brady's NSF project when he was at the University of Arkansas. This is Mung down in the valley communicating during Hispanic Week. Were you speaking Spanish?
No.
Okay. Just checking. This is, I don't know about a Spanish-speaking Taiwanese, what would come out, huh, in terms of the accent. This is a summer camp in Colorado that they don't have anymore, but we used to participate. That's you, isn't it, Robert? And is that Cecil? This we really enjoyed. And we had 2 shakers out there, but only one was allowed to go near buildings, and that was on the Stanford campus. So we shook all over the Stanford campus. And 20 minutes to go, okay. And I really had some really interesting things to say there, but whatever. No, here's Liquidator on top of Yucca Mountain. That's in the Mississippi embayment. We need to go deeper there. We could double at least. Salt Lake Valley, Hanford again, profiling, and you'd be surprised if you go along a high wire or high voltage wire, it takes over Liquidator. Oh yeah, the shielding, the geophysicists don't put shielding in these things. It takes them over. It's shaking at 60 hertz. There's nothing you can do about it. So we got to get away. Here is Palo Verde. That's the biggest nuclear power plant that we have in the United States near Phoenix, and we were helping do some work. That's how we get program income. So we don't rent it, but we charge them rates. NSF wants us to do that. Then that we're allowed to keep a certain amount of the money to improve the equipment, just to improve the equipment, and we've done that for you. Next. So these are some of our workshops. We won't worry, but we did the levee, and we were trying to move along the levee. We didn't, but I mean, the idea is we would like to be able to move and do the testing on the move, because we have rollers that we could have bigger rollers that could go down along the soil and then find the problem spots and then maybe do other types of testing. So screening and then more improved. Do liquefaction work. You can't put bridge in your program to NSF right now because the computer will look for that word, and if you put that in, it'll kick it out. You will not get funded because the Federal Highway Administration now is supposed to fund the bridges, not the National Science Foundation. So you have to be tuned into some of these things. When we put our proposal together, bridge wasn't a dirty word, and so there we showed it. And this was done, we didn't get the money, Nadad Kagunski got the money, and he did it, I don't know, magically, and so we were able to test a small bridge. It was over the interstate highway. Next. This is, you're going to see the proof of capability workshops. And we put this in our proposal because if you don't hear about it, you just can't read a little something and get a sense for what's going on, huh? And most people sit behind a desk and don't get out in the field. So you don't have a feel for what you might try to do. And we had a very nice liquefaction workshop out in Portland as our first one. Go ahead, Robert. And, in our science plan, that's a higher resolution, 2 and 3D imaging. We need to do that. Now, that's in the program. That's not us doing it. That's us trying to get things ready so other people can do it and we can work with them. Next. This is Brady's work. It was a rapid, so, that's a small amount. Relatively speaking, $200,000 or less. And then the New Zealanders, for our liquefaction rapid, contributed another $800,000 in the end because it was working so well that they kept going. But this was not known. That period at the site was not known. Next. So before that time, if you need to correct me, go ahead and jump in anytime. Before that time, so here's a profile, and they were down in the top 50 meters at most, I think. And the deepest well was 450 meters, and they still didn't run into bedrock. Next. Brady went down there, took T-Rex. Really, it was both projects that worked to get T-Rex down there, but it was used down there next. And one of the big costs was all of the moving time. We were there for a couple months, and just having the truck come and move it from site to site turned out to be really expensive. So 15 different sites. This just is the Christchurch area next. And is this Queen Elizabeth II? Do you remember that QE2?
Yes, yes.
This stadium?
Yes.
And it underwent, in fact, I think you see a lot of sand boil material there. But you can see there's an active source. The C would be the passive source, and the different arrays. And so the active and the passive were combined. Next. And so so this isn't my plot, so for sure it's in meters. Mine might have feet there. But I mean, you're looking at the shear wave velocity profile that they never had before. And there was a maximum shear wave velocity profiling depth. I remember Brady coming in my office and saying, well, they think it's bedrock. Do you have any equations for gravels? You betcha. And we proved to them that gravels could have that velocity down at these depths. Now, we've never been down at those depths, but our equation said that's what it would be. And I feel strongly those are good equations. But this just shows you work also that Brady did on the supercomputer as possible solutions and uncertainty associated with the different solutions. So that worked out very well. Next. Here we are out in Yucca Mountain, and NSF didn't fund any of this, but this is program income. There's T-Rex. We're shaking this footing. Now we just use the base plate, but at that time we thought we needed a footing in shear, not in dynamic, not in vertical motion as much. In fact, I'll ask a question. Anybody that knows the answer, I would love to be educated. How does Poisson's ratio vary with strain? Who wants to go? Who wants to go first? Yeah, we don't know. We don't know. I mean, see, we have run, of course, what seismologists typically do. This is G log gamma. They have constrained modulus log gamma do the same thing, meaning Poisson's ratio is constant. Okay. We have done with T-Rex on a different project. This is G log gamma. Now we can't get out but about to 0.08% strain. So we're not going to high strain, but we're going out there. And in constrained compression, so in the plate, looking at how it's going, if that would be the modulus. Sorry, I didn't mean it to go down so much. That's what constrained compression did. The modulus, the Poisson's ratio, if you defined it that way, is not constant. But we didn't get very far along before the military took my PhD student away. He got his degree, but we need to get it to do this. This was on cemented alluvium. This is what the lab would tell you. Mung did some work with smaller grains than this, and that's what the field did. And so there's a factor of 3. There is some nonlinearity, but that's right near the surface. But there's nonlinearity, and you would be in a mess. Now, let me say one last thing, and it's very interesting to me. The Bechtel people who were designing the pads for where they would, this is at Yucca Mountain, where you would exchange the canisters, and they would be processed and this and that before they went down. They had no idea how stiff the material would be, and they used shear modulus to calculate the modulus, the modulus of the soil in terms of as you loaded it, how much it might deflect is very stiff. So they could use that, and they didn't have to go any further. It wasn't near failure at all in this slab, but they were designing the slab, and they had nothing to use before this. They were very pleased. Next. This is, we won't go into all the details, but a lot of bad things happened in Christchurch due to a series of earthquakes. Next. They were doing shallow ground improvement, trying to make a 3-meter thick layer. Does that mean I'm 10 minutes overdue? I mean, I've talked too long, or I still have that left? Okay. Rapid impact compaction. That just means beating on a 1-meter diameter steel plate with a ram and compacting and trying to get the top 3 meters, maybe 4 meters to be densified. This shows rammed aggregate piers. The way they were built, they're built with just coarse gravel. This shows low mobility grout. Those looked a lot like that. Yeah, that would do that. Nothing. No low mobility grout looked like that, but that's okay. Next. So don't worry about these. That's not what they look like, but that's to indicate here's a rammed aggregate piers. We would put T-Rex on top. First, we would install sensors, and then we'd put T-Rex on top the next day and shake. And there are the piers. Those will be pore pressure transducers. Those are 2D to start out with, geophones. Next. Aha. And we'll just shake and make measurements. What happened? Here we go. Ah. We don't have, okay, this is the head of the, we don't have a volume, do we? Okay. Well, he's saying that they have problems and blah, blah, blah. And we're trying to thicken the crust. No, he's very, very nice person, by the way. Very nice. This is Sjord van Balague, who's really good. There's Professor Stokoe, who's nervous. And he's, oh, look, oh, there's a downward going shear wave. Wait a minute. There we go. And there's T-Rex over there. There's our field hunk of junk. Oh, that Volkswagen wouldn't necessarily go forward when you put it in first gear. No kidding. But we survived. So we're setting up. Oh, liquefaction right there. Where is it? There it is. It was just a little, it wasn't really. It was just some localized, a lot of rain, and the water popped out of there. We couldn't really get it to liquefy. They were very happy. They were very happy. The consulate, the ambassador in Washington, D.C. wrote a letter about this, and the University of Texas to NSF. They were very happy with what we did down there. Can we pop to the next one?
Absolutely.
Okay, and this is just shaking around buildings and bridges. And see, there's one of the machines. I think that's maybe Liquidator. See those cables? There'll be cables, and we'll be pulling stuff over. Because, go ahead. And, you know, the idea is here, okay, the structural guys, they can test in the lab, but it doesn't really represent the field and the complex conditions in the field, so you need to go test in the field. So we're trying to convince the structural people to do that. Okay, this is a video that's important. This is, so this Sharon Wood, this was our first project that we had before it really started. And we're building quarter scale, I'm using the term we loosely. We're building quarter scale drilled shafts and a bent on top of those that represents a real bridge in California. And we'll be shaking those, and there'll be a bent that's taller, and this is the taller one, and you'll see over here a bent that's shorter. And you'll see there's Thumper shaker right there. We're just, you can shake, and it showed you in one slide, you can shake all directions, you know, around this bent to see how it responds to different earthquake motions, vertical and horizontal. That's just horizontal shaking in all kinds of locations around it. Okay, now, there's Thumper, so it's taken off the truck, bolted to the top of that. Now, you probably think that that's such a small little shaker, it can't do anything. That's a quarter scale. That's not tiny. It's even gapping, okay? We'll get more gapping when we start pulling on it. But, oh, no. And cracks, it was causing a little bit of cracking in those. There's a shorter bent compared of the two bents. And, you know, now we're pulling because one of the guys at Davis, a nice person, I won't name him, but, you know, said, well, this stuff doesn't do very much for us. Okay, what do you want us to do? So we have created hysteresis loops under these conditions, and it's cracking, huh? And I don't think anyone, even the guy that wanted us to do it, has used the data. I think all the data is there waiting for some smart, yeah, that's gapping, one good PhD student or two to analyze this data to come to the next generation of how things are going on. So you tell me I don't do enough cracking, huh? I'm talking to the guy now at Davis. I mean, you don't worry, we'll do more. But we did back and forth. You got two machines, so you can do back and forth. It doesn't just have to be one-way loading. And that was easy. I think that's Sharon, by the way. That's Sharon Wood right there. Is that Ellen Rathje? That was Sharon, wasn't it? Okay. Okay, well, straighten it up. That's just the winch powered by the hydraulics on the machine. The machine's, got the brakes on. And I think the structures people have a lot there to use. This is just saying, okay, the thing that you always think, if you can put known forcing functions at different points around the bridge, that's got to be a lot better than just ambient, looking for localized defects in the bridge. Remember, we went down in smoke, but that's what we thought. And that's what we still think, and that's what that illustrates. And with Liquidator, it can even go lower, huh? And we could, for the appropriate project, try to orient it horizontally. We'd be happy to do that and see if we can't excite at very low frequencies. To us, that means 0.6 hertz or something. Can we speed through that? If we can speed through that, but that's just showing it going around the building, and it can go, and this could be put up here or put in there with the truck just out there as a pumping mechanism. So you've got your pump there with you if it can't fit in the building. That was before any NEES, and that was a bridge that's being decommissioned in Texas, and we put the RDD on it, and I was standing down here, literally, I was standing down here looking at it, and this was just vertical because that's all that could do. And the column was doing this. I mean, it was moving this much. And I said, Stokoe and a bridge falling on Stokoe, this would make big news, but I don't want to. I got out. I mean, I chickened out because it was a bit frightening to see how much motion. And this is a small machine. I mean, a moderate sized machine. Next. Brady did this when he was in Arkansas with his Thumper. So he built a little bit bigger one, mainly from the cab and stuff like that on the boat. But with a structural engineer, those are the different modes of that bridge that they were investigating using Thumper around the bridge. Next. I don't know all these. These are just, Mung, do you want to say anything?
Yeah, just tell you that you can put your own sensor. If you try the post, you can put your own sensor, or you can process from our sensors. And we don't have all the sensors. We don't have those kind of strain gauges and stuff like that. That you probably have to use your own in that case.
Yeah. Okay, next. So this is on our web page. This is probably this is real. I mean, on the web page right now, and it just shows you this is. We won't worry about all the details, but if you had NSF, that's what it would cost you. I guess the next one. That's what it would cost you if you did it without NSF. So NSF is giving you a lot of support. Whether everything is, it's all there for you to see. We'll answer any questions that you want. The overhead is now 56.5. It does minor, but I mean, we're trying to help you estimate your project. Next. So you can contact any of us. that is Rathjes, isn't design safe. That's where all the data resides. And we thank you for your hospitality, the University of Florida.